And hello, welcome to this video. So in the last video, we actually talked about how to quickly import data arrays via CSV and perform a non-uniform fast Fourier transform on them. So MATLAB and FFT is what you usually search for. Okay, and this is where you have your function. So if you have a non-uniform sample array, okay, you can perform a fast Fourier transform given this, what do you call it, let's say your Y array. Okay, let's say you have this sine wave thingy, and then your Y values will be the Y values of the sine wave, and then the X values will be whatever you have at the bottom. Okay, or in this case it's like time. Okay, so that's what you'll do for your non-uniform fast Fourier transform. Okay, so I'm only going to cover like the first usage of this. Okay, but you have your most basic non-uniform fast Fourier transform of a column vector X with another column vector T, where T represents your time or your x-axis. X actually represents the vertical axis, sometimes called y-axis, but I don't want to call it y-axis here because there's another y vector right there. Okay, so alright, the question is, okay, next thing you want to do is kind of plot this thing, right? You want to plot this thing out, and I've already explained in the last video. If you want to get a plot of like magnitude versus the frequencies, you'll need to perform some sort of a square Pythagoras theorem kind of thing just to get the hypotenuse, which is the actual magnitude. And of course you do some arctangent thing to find, because this is a complex number, you do some arctangent thing to find the phase. Okay, so that's what you do with your to get the phase and the phase and magnitude of your Fourier transforms, just like what I was saying in the last video. Question is, what then are your frequencies, right? So you have your phase, which is the angle here, the amplitude, which is described by this length of the complex number. What are the frequencies? Okay, and omega equals to 2 pi f. I mean, that's just a reminder for you. Okay, so normally in a Fourier transform, you'll see this. You see this kind of a peak spectra, whatever, I don't know how. And then right over here in the center, we have this thing called the Nyquist frequency. Okay, I won't go through too much. I assume you know. And then you have a sort of a mirror image right over here. Okay, and this is your sampling frequency, and the Nyquist frequency equals to the sampling frequency over 2. Okay, so for the most part, if you want to take a look at frequencies, you actually look at the left side, because that actually represents sort of the real frequencies. All right, this is the in a sense, if you have a sine wave like this, all right, and maybe this is like what, 0.1 hertz. So this is a 0.1 hertz sine wave. Okay, but a sine wave can also be like this, and this over here, and this is also a 0.1 hertz sine wave, right? And both of them are 0.1 hertz sine wave, but this is like the opposite. So this is both of them are of the same frequency. It's just that they're kind of like 180 degrees out of phase. So this the right side of the Fourier transform plot actually describes this phenomenon here. Okay, you can think of it as a negative frequency, because a negative frequency would be something like this. Okay, alright, negative frequency. Let's go. Yeah, so if you have a sine omega t, all right, so if that's the positive side of the sine wave, all right, you can also have sine minus omega t. So this is what negative frequency is talking about. It doesn't make sense physically, but when you put it mathematically, now you will see that, okay, I have a minus sign here. What does that mean? It means in your what do you call that? How do you say? In your 4 quadrants, okay, you sort of have this kind of a negative angle. Okay, if you can have negative angles, you sort of can have a negative frequency as well. Okay, negative frequency, the easiest way to explain it is it just means it's like 180 degrees like out of phase. All right. Yeah, so I think 180 degrees out of phase, or it's just like inverted. Okay, it's a little bit more difficult to imagine, but the basic principle is just to, wherever you see this frequency here, just substitute the negative version of it and plot it into the sine wave, and that's what your negative frequencies are talking about. Okay, so enough of that. Okay, so that's just a refresher on what the plots look like. Okay, so you have your sampling frequency and your Nyquist frequency. Alright, problem is, of course, when you have a non-uniform fast Fourier transform, you will not have a so-called sampling frequency, right? So let's say you have time equals 0, time equals 0.1, time equals 0.3, 0.6, and then you have all sorts of data here. Okay. And now how does the algorithm actually work, and how do you then determine which frequencies to plot your magnitudes of your Fourier transform against? Alright, so when you have something like this here, okay, the standard way, okay, the standard way that this non-uniform fast Fourier transform work is basically to, okay, assume that you want to have your frequencies evenly distributed. Now, what do I mean? Okay, normally what you do here, okay, 0.0, 0.1, 0.3, 0.6, okay, ideally in a normal Fourier transform, you have 0.0, 0.15, 0. Okay, hold on, I got it wrong. Okay, let me zoom out. Ooh. Yeah. Yes, 0.2. Oh, no, I was using the zoom tool. Okay, let me get this back. Okay, 0.2, 0.4, 0.6. Right? This is in the normal way. If you have a evenly sampled kind of a data set. Okay, so you sample at normal intervals. Okay, so normally your sampling frequency here, let's say, will be 1 over 0.6, or 1 over 0.2 rather, 1 over 0.2. And their sampling frequency then will be, I think, 5 Hertz. 5 Hertz. Okay? So what will the non-uniform fast Fourier transform do? It will take this array, okay, it will take this array here, and what it'll sort of do, okay, what you'll sort of do at different intervals is that it will try to interpolate the data at these points. Okay, it will try to interpolate the data at these points. So for example, 0.2, you can kind of guess it by linear interpolation for the from data points of 0.1 and 0.3. You can sort of linearly interpolate that. And likewise, 0.4, you can actually also linearly interpolate between the data points 0.3 and 0.6. Okay? So basically, the non-uniform fast Fourier transform, you can sort of do some guesswork, okay? Convert a conveyed a non-uniform kind of data set, and then you just put the linearly interpolated data into an even sort of data set, uniformly sampled kind of data set. So these are some ways that the non-uniform fast Fourier transform works. Yes, and if you're not sure, you can always just look online for the non-uniform fast Fourier transform algorithm. One of these, you can just open these links and you'll find that, okay, the basic idea of interpolation is there. For example, this, okay, you can just look, for example, Dart and Rocklin method. This is one of the ways. Okay, I'll put all this inside the description. Okay, so you see here fast Fourier transforms for non-equispaced data, and this, it basically says that there is interpolation. There's this idea of interpolation. Okay, interpolation is here, and how you interpolate, that's really there are more nuances to that, but I'm not going to get into it. But I'm just going to leave these links for you. Basically, by Google search, you can just find this out. But the idea is the same. You interpolate the data points and then you sort of plot values here. And once you interpolate it, once you interpolate it, the next step is just to do your normal FFT, normal fast Fourier transform, and then you will churn out your data. Okay, so how does that help us? It will help us to sort of guess what a sampling frequency should be. Okay, so for example, you have the original pieces of data, for example, was 0.1, 0.3, 0.4, and 0.6. Okay, these are non-uniform sample points, non-uniformly sampled points. Okay, so this does not have a sampling frequency. But suppose for a moment that you try and shift everything to become more uniformly sampled. What will the sampling frequency be? Okay, so the sampling frequency, like I was demonstrating just now, it's 1 over 0.2 Hertz. Okay, how did we get 1 over 0.2 in the first place? Or how did we know what's the even spacing, so to speak? Okay, how did we know what the even spacing was? Alright, okay, I think, shucks. Yeah, I think I made a mistake just now. It was supposed to be, you're supposed to start at 0.1, okay? But, okay. You're supposed to start at 0.1. Yeah. You're supposed to start at 0.1 and then you sort of evenly space. Yeah, so, I mean, the idea is the same, okay? Alright, so I was talking about these data points. They start at 0.1, 0.3, 0.1, 0.6. And then we try and make these data points uniform by doing some interpolation technique. Okay, I should have used 0.1 seconds as my first data point, and then evenly space up to 0.6. So a kind of mistake just now. I put 0.0 seconds as my start point, which was kind of off. So we should start at 0.1. But idea is the same. Okay, from 0.1 to 0.6. How do you do this even spacing? Okay, it won't be 5 Hertz anymore. Alright, so if I were to evenly space from 0.1 to 0.6, how do I do it? Okay, so what I'll do is I take 0.6 minus 0.1. Okay, and how many points do I want? Okay, I want 4 points, right? I want 4 points. Alright, so let's see whether this works. So 0.6 minus 0.1, that's 0.5. 0.5 over 4, it becomes 0.125. Okay, let's see whether this works. Okay, 0.1, okay, equals to this plus 0.125. And you add 0.125 again, 0.125 again. Okay. Okay, and then, okay, it looks like now I have 5 data points. Okay, so I have 4 data points here, but if I were to use this 0.125 spacing, I'll have 5 data points. So that's not correct. So what I'll need to do is basically take the number of elements in this array, I'll minus 1. Okay, so how do I do it? So 0.6 minus 0.1, this is actually 0.5, and then I'll divide it by 3. Okay, so I put D3 plus 0.5 divided by 3. Okay, 0.5 divided by 3, and let's paste this data down. And you take a look. 0.1, 0.2667, 0.433, and finally 0.6. So the way I get my frequency is, okay, the way I get my even spacing, see, you start with 0.267 here, 0.433. Okay, pardon the handwriting, let me try again. 0.43. I'll just do 2 decimal places because I don't want to write too much. Okay, so how do I get the so-called time interval here? Okay, I actually took 0.6 minus 0.1 and I divide by the number of points minus 1, and that will be my so-called sampling interval, delta TS. All right, sampling interval. Okay, so what's the sampling frequency? The sampling frequency is equals to 1 over the sampling interval. Okay, so for each frequency bin, okay, let's say I do a fast Fourier transform and I need a frequency array. Okay, I need a frequency array to plot this so-called output against. All right, so I have all this output data after I do a fast Fourier transform. Of course, this is a raw data. Okay, I just left dashes down there as a placeholder for raw data. So after you perform a FFT, okay, after you perform a FFT on them, and what happens? You'll have your fast Fourier transform of this data. Okay, there'll be 4 pieces of data. Okay, so where is your first so-called frequency? Your first frequency is actually 0 Hertz. Okay, 0 Hertz, which is called the DC frequency. Then everything after that, how do you actually get the correct frequency? So you step it up. Okay, you step it up. Okay, you step it up in this manner. Okay, it must be such that your last what do you call that? Your last column, your last data set must correspond to the sampling frequency. That's the maximum frequency you can go, and it sort of corresponds to the rightmost point. Okay, and then over here in the middle, of course, you have your Nyquist frequency and whatever else is in the middle. Okay, so if your Fs will be your last data point and 0 will be your first data point, okay, how do you if you want a even so-called spacing of frequencies, okay, and usually Fourier transform, fast Fourier transform will make sure that you have an even number of frequencies that are being sampled. Yeah, usually for fast Fourier transforms, they will sample your sine waves, so to speak. You sample the frequencies at even frequency intervals. Okay, and your first frequency is of course 0, and your final frequency is like your Fs. Okay, your sampling frequency. Then you have all these other things in the middle. How are you supposed to determine the steps over here? Okay, so the steps over here, okay, your steps over here are as follows. You have Fs minus 0 over, how many points are there here? There are, we can call this number of points n. Then you just subtract 1. Okay, you just now we used the number of points here, which is 4, and then we subtract 1. Now I'm going to generalize. If you have a n number of data sets, you just subtract 1. Okay, of course, if n is very big, it doesn't really matter whether or not you subtract 1. But for sake of accuracy, or for sake of accuracy, it's good to just subtract 1 to see what you're sampling, to see where you should be doing with this. So anyway, if this n here, if it is the number of elements in your fast Fourier transform array, of course, if n gets very large, it doesn't really matter whether you use n or n minus 1. Okay, so what I guess most of what you'll see is fs over n to be this the spacing between each sampling frequency. Okay, so you start from a frequency of 0 and then you kind of space it out. Okay, so you kind of space it out like that. And of course, for real data sets, you have thousands of points sometimes, so or 100 plus, 500 plus points. So for all intents and purposes, fs over n will kind of do enough. So this is a rough intuition. I won't say it's 100% correct, but that's a easy way to think about it. Okay, so I think I don't want to take too much time, but this is just some background into how non-uniform fast Fourier transform, the thought process behind it, and hopefully now we can apply this thought process into our MATLAB code and kind of see what it's trying to do. Okay, see you.